In section 2 of chapter 1, we'll be having a look at how to define a thermodynamic system and the properties of different types of thermodynamic systems. When you've watched this video, you should have attained the following learning objectives, meaning that you should be able to first define a thermodynamic system, the system boundaries, and the surrounding environment. Then you should be able to identify different types of thermodynamic systems, namely isolated systems, closed systems, and open systems. And finally, you should be able to apply meaningful system definitions to typical components in thermal energy systems. So first of all, preceding any thermodynamic analysis, whether it's a numerical or an analytical analysis, we'll first have to define the system boundaries, and the surrounding environment. In thermodynamics, the term system refers to the collection of matter or region in space which is to be the subject of the subsequent analysis. A generic sketch of a system could therefore look something like this. Now here, everything that lies within the line is what we define as the system, while everything that resides outside the line is what we define as the system's environment. The partition between the line and the environment, in this case the line, is the so-called system boundary, sometimes also referred to as the control surface. Now, an important feature of the boundary is precisely that it is a surface, meaning that the boundary can have no thickness and therefore cannot contain any mass or fill a volume in space. This means that the boundary itself is not another system, but a sharp partition between the system and its environment. A consequence of this is that the properties of the system and the environment are shared exactly at the boundary. Now, it's often tempting to choose the physical boundaries of a component, such as a wall, as the system boundary. But here it's important to remember that a physical wall will have a thickness and contain mass, and is therefore not a surface. One way of dealing with this is to define the wall as an additional system itself. Other solutions will be presented in the examples at the end of this video. Once the system boundary, and the environment have been defined, it should be identified how the system interacts with the surrounding environment or adjacent systems. Generally, a system can interact through three modes of transfer. It can interact through the flow of mass, through the flow of heat, and finally through the flow of work. Now let us first assume a system boundary that is impermeable, meaning that there will be no transfer of mass to or from the system. Rigid, meaning that there will be no transfer of work to or from the system. And finally, adiabatic, meaning that there will be no transfer of heat to or from the system. Now in this case, we'll have what is referred to as an isolated system. Now, as a consequence of the conservation principles, an isolated system is a system of both constant energy and constant mass. Isolated systems may serve as a relevant idealization for the analysis of fundamental thermodynamic processes. However, isolated systems are rarely relevant when modeling actual thermal energy systems. So let us instead assume a system boundary that's still impermeable, but will allow the transfer of both heat and work. This results in a system that is referred to as a closed system, or alternatively a control mass. The term control mass refers to the fact that based on the conservation principles, the closed system is a system of constant mass. However, as the boundary allows the transfer of both heat and work, the closed system is not, like the isolated system, a system of constant energy. Now, closed systems occasionally occur when modeling thermal energy systems. However, this is often only for a part of the process that eventually ends with the transportation of mass to or from the system. And often these situations can be avoided by an alternative definition of the system. So let us finally assume a system boundary that allows all three modes of interactions. This results in what is referred to as an open system or a control volume, referring to the region of space that is the subject of the analysis. Now, it should be noted that it is not a criteria for the control volume that the volume of the system is constant. The control volume may change size and location if necessary. Since the open system will experience both flow of heat, work, and mass, then both the mass and internal energy of the system may change. Now, most components applied in thermal energy systems are best described by defining them as open systems.